Welcome back from the break. We heard about how to survive wipe coding time, and now we see how you can provide those tokens and feed the agents. Thank you, Antonio, for joining us.
Thank you. Hello, everyone. I'm Antonio, work in Red Hat in the Inference engineering org. I'm not the host for the talk that just happened on stage. But this is going to be about distributed inference with llm-d on Kubernetes. Before starting, how many of you know llm-d? Okay, like better than last time. Okay. Here's the agenda. We're going to go through, what is llm-d, why we need llm-d, and of course the challenges that llm-d solves. And then we're going to go through inference. So what is inference? The different phases of inference, an architecture overview, and then the well-lit path of llm-d, which are ways of deploying llm-d. At the end of this, we're going to go through a live demo where we're going to deploy llm-d using the intelligent inference scheduling well-lit path. And I hope I'm going to show you something interesting. So what is llm-d? llm-d is of course, an open source framework for distributed LLMs inference that runs on Kubernetes. It is a joint effort between Red Hat, of course, Google, IBM Research, NVIDIA, and many other organizations. The thing is here, the vision for llm-d is any model on any accelerator on any cloud, because right now the scene is pretty different, like the scenario that you could have when you deploy LLMs, right? So we need something that you can use with any model on any accelerator. Accelerator is just a GPU, for those that don't know, on any cloud, because we want to avoid vendor lock-in, right? And llm-d is part of this story. llm-d recently joined CNCF as a sandbox project, so that's just talking about trustworthiness, which I think was a big theme in the last talk as well. We're trying to do that. So why llm-d? I think at this point, most of you are using AI to write code or do everything or everything and anything. And you use AI token providers, right? I mean, you use Anthropic, you use OpenAI, Google, Gemini, all those things. What we want to do with llm-d is to enable organization to move, to enable them to move from being token consumers to token providers or producers. Still, because we want to avoid this vendor lock-in, so we want organization to be able to host their own AI, to have ownership over what they serve and how they use their models. Just to give you like a little bit of a map where llm-d stands, we have the accelerators on the very bottom. Those are the GPUs doing the hard work. We have the inference service, like vLLM, for example, but llm-d also supports SGLang. We have the models that you're serving on the accelerators. And then on top, we have llm-d, which integrates Kubernetes. And it's basically, you might have heard the term AI gateway, but this is a little bit different. llm-d employs optimizations, distributed optimizations to serve LLMs. So basically to achieve better throughputs, lower time to first token, inter-token latency, things like this. So the question arises like, why? Why do we need this, right? Because in Kubernetes, we already have primitives to solve the challenges that we have with LLMs, scalability, reliability, speed, and efficiency. I mean, Kubernetes was born for serving the traditional web application case. So why can't we use the same tools that we had, like load balancers, all these kind of things? Because essentially, like web applications are very different than LLMs. With web application, usually like you have requests which are fast, uniform, and cheap. They're going to hold up, like when you receive an HTTP request, they're going to hold up a server for like 200 milliseconds, maybe even less. So if you deploy a web application and you put in front of it a Kubernetes load balancer, which is a pretty standard, deployment, you end up having a pretty even load on your servers, on your pods, and that's good enough. Like, you don't need anything else. AI is a bit different. LLMs, I must say, is a bit different because LLM requests are stateful because they depend, of course, on previous bits of the conversation that you were having. They're latency sensitive. They don't take 200 milliseconds. I mean, if it's served good enough, they might take 200 milliseconds, but usually they could take more than that. And they're really expensive because running these GPUs to do inference is really expensive. So every performance gain that you can get is actually very important here. So if this is not enough, like to convince you that we need a new type of load balancer that is aware of LLMs, we need to talk about a fundamental concept in an LLM serving, which is inference. Inference is basically the process of generating tokens, right? Like you get a model that has been trained, you do inference on it, so you predict the tokens. You get the answers, generative AI. It's all about inference. Inference itself is split in two phases, prefill and decode. In the prefill phase, the model takes the whole prompt, looks at the whole prompt in parallel and generates the context, looking at like token by token, all in parallel. So this phase is very compute bound, it's compute intensive. So the length of this phase depends on the tensor core flops, how fast your GPU is at crunching numbers, pretty much. Decode is the second phase, and prefill generates the first token. So when you get you give an LLM a prompt, it does prefill. At the end of the prefill phase, the output is one token, the first output token. Decode generates one token at a time, looking at all that was generated before. So it looks at the context produced by the prefill phase, and the output is just one token long, and the input is just one token long, because it just looks at the last token. This means that this phase is memory bandwidth bound, because the input length is very short, just one, right? So the most of the time that you will be spending in this phase is moving things from memory, from the high bandwidth memory of the GPU, like the KV cache and the model weights, for the tensor core. To the tensor cores, so that the weights are available to make the required computation. And decoding, going over all the tokens that you have in the prompt, it's a very taxing thing for the GPU to do. So that leads us to KV caching. Basically, what KV caching is, as the name says, we're caching everything that we have produced in the prefill phase. So instead of re-going after each token in the prompt in the decode phase, we just query the cache. We get the KV values that we cache from the self-attention layers of the model when doing inference. And this speeds up significantly the process, because otherwise you would have to recompute everything, like we said. Of course, there is a catch. It takes up a lot of memory. And as the conversation gets longer, you eat more memory. That's why you have limits on things like the context on LLMs. You have a certain fixed context, so certain model can be 256K, 1 million tokens because of the KV cache, because otherwise the size of the KV cache becomes just unmanageable. It is one of the reasons why, but it's mostly the main reason. And this is basically what we do in inference to make modern LLMs usable. We trade memory capacity for speed, because we make use of this cache. And this is also where llm-d comes in. It's basically the main optimization that we can do with LLMs, among many others. So now that we spent a bit of time looking about taking a look about inference, we can do a bit of overview of the llm-d architecture. When a request comes in to the inference gateway, and the inference gateway here is just a normal gateway that implements the how's it called? Gateway API inference extension specs, Istio, all of them just implemented. But when a request comes in, instead of doing like a blind decision or just a normal round robin decision like you would have in a normal Kubernetes load balancer, the routing decision gets delegated to the inference scheduler, which has been recently renamed to router, but doesn't change anything. The inference scheduler is LLM aware. What does it mean? It doesn't look at just things like the load in terms of CPU and memory, but it scrapes, for example, the model servers like vLLM for real-time metrics to know which pods hold which KV cache blocks that we might need to fulfill our request. So by knowing this kind of information, it can do an intelligent decision about where to route that request. So the inference scheduler gives back the execution flow to the inference gateway, telling it basically like route this request to this pod because it's the best pod that we can route the request to because it has this KV cache blocks and etc. And then the inference gateway routes the request to the actual pods, and you get your response back and everything. This looks simple. It is simple actually, but it's the most foundational optimization that you can do in inference, in distributed inference. Also, it's foundational for many other things that you might want to do with llm-d, which is like prefill-decode, which we're going to cover in the next slide in a short bit. This slide is just to give you a taste of the gateway API extension for inference. They basically introduced this new CRD called Inference Pool. This is somewhat similar to a Kubernetes service, but instead, like a Kubernetes service usually gives you like a stable IP for pods that are serving maybe the same application, same API. Inference Pool does the same thing, but for models. So it groups pods by model served and hardware. So you can deal with complex, multi-model, multi-accelerator environments. Now on the well-lit path. Like I said, llm-d uses this terminology in the community called well-lit path. What are they? They're just like validated blueprints for deploying llm-d. First, we're going to cover the intelligent. There are many more on the llm-d website, but I just decided to cover 3 because otherwise this talk would last like an hour and a half. The first one is intelligent inference scheduling, which is what we just touched on. So it's KV cache aware routing, pretty much. A second one is tiered KV caching. Basically, the problem that we just touched on, as the conversation gets longer, for example, for a normal chatbot application, the KV cache usage rises and you run out of memory. How to not do that? You offload some of this KV cache to the CPU memory, so RAM, and local SSDs, for example, so file system. And then last, we're going to take a look at PD disaggregation. Okay, first one, intelligent inference scheduling. This is the most simple way to deploy llm-d. What it does, it takes a look at 2 things mainly. It does load-aware routing, so it looks at which are the pods that have the lowest load in terms of like queue size, normal load balancing stuff. But it also takes a look at KV cache utilization, because like we want to route requests to the pods that have the lowest KV cache utilization, because we already know that the conversation might get longer and longer, so we want to have space for that conversation to happen. Otherwise, we might get like a KV cache eviction, and it's going to slow us down, and it's not very good for the experience. And then we have prefix-aware routing. This, like I said before, takes a look at which pod has the blocks that we need, so that we effectively we can skip the prefill phase because we already have cached all that information, and we don't have to recompute it again. Of course, they don't count the same. They weigh differently because llm-d has this like set of configurable filters and score, which you can assign to different weights. So for example, the load-aware routing weighs a little bit less than the prefix-aware routing because, of course, we want to be quick. This is just to give you, I mean, not some numbers, but like graphically to see that, the round robin case, which is the blue line, the inter-token latency, which is like the time between like every token during the decode phase. So when you see like you're talking to ChatGPT or whatever, you see like tokens are appearing very quickly. That's the inter-token latency. And you can clearly see that with the round robin approach, we don't make use of the KV cache knowledge. And the inter-token latency goes higher and higher and higher. With llm-d deployed, we actually know which pods are holding the KV cache blocks that we need, and we can achieve far better results. Same thing goes for the time to first token. Again, time to first token, it's dominated by the length of the prefill phase. So if you have that cached, it's going to be almost immediate. And with a round robin approach, we don't make use of this. And again, we're slower. And this is just the throughput. I mean, this speaks for itself. The red line is better because we spend less time recomputing things. Then we have tiered KV caching. As I was mentioning, one of the problems, again, is holding all this memory, right? So the GPU VRAM, even if you have a lot, you run out pretty quickly, especially if you're serving a lot of users. So by leveraging the CPU RAM, which is mostly in use, when you run a vLLM server, a model server, the GPU VRAM is used a lot, of course, because you have to keep all those weights for the model in the KV cache. But the CPU RAM doesn't do anything. It's mostly idle, and we can actually use it to offload some of the KV cache. Same thing goes for storage. We can do the same kind of offloading to our local file system, whether that's like a CephFS or OpenEBS, whatever. You can just use it, and we can leverage that as well. This is actually very important, even if it seems like just a stupid gimmick to do and something very obvious, because when you get KV cache eviction, that's a big slowdown. So the more that we can hold, the better it is. And you can see, again, graphically from this graph, the purple, no, sorry, the blue line is GPU only. You can see that throughput decreases very sharply far earlier than if you're using GPU plus storage or GPU plus CPU offload. So I mean, here it's like 14 times whatever. I don't know how exactly this was produced, but I mean, it makes sense, right? If you can hold more KV cache, you're going to have better throughput. PD disaggregation, something that I wanted to touch on. It is very interesting because one of the other optimizations that you can employ with llm-d together with vLLM is prefill-decode disaggregation. How many of you know about tensor parallelism, or maybe have heard of it? Okay. Tensor parallelism is how you deploy your model on the GPUs. So tensor parallelism 1 means using one GPU for one model. So all the model weights, they get loaded up into one GPU. If you use tensor parallelism 2, means you're using two GPUs for the same model, for one model. That means basically like you're sharding the model weights between two GPUs. Why would you want to do that? Because the decode phase, as we said before, is memory bandwidth bound, right? It's not memory bound, memory bandwidth bound. So the majority of time in that phase is just loading those weights and KV cache on the tensor cores. If you have more bandwidth, because you're using multiple GPUs, and effectively, if you use two GPUs, you're doing like ×2 in terms of the bandwidth that you have, you're gonna have better latency. because effectively you're using more hardware for the same GPU. So coming back to PD disaggregation, what does it do? It enables you to have different workers, different topologies for the pods that do different phases of inference. So you can, for example, have, here it's not mentioned, but for example, 8 prefill nodes with tensor parallelism 1, because when you're doing prefill, what's important is prefill is compute bound. So what's important is like the velocity at which your GPU can crunch numbers. So you don't want any interruption, right? You don't want to spend time loading things from memory. You just want to have those tensor cores working through the computation through the tokens. So you can have, like, as I was saying, like 8 GPUs with tensor parallelism 1 dedicated to doing prefill, so they can go as fast as possible. Maybe you can have like newer GPUs as well, because they're better at tensor flops, have more tensor flops. And then maybe you can have like another pool of pods with, I don't know, 4 GPUs per model, so tensor parallelism 4, which increases memory bandwidth and hence increases inter-token latency. So you have the best of both worlds. Like, otherwise, optimizing for one phase or another is very different, because you cannot have a mixture of those. But with PD disaggregation, you can. How does this work? Basically, when the request hits the gateway, of course, the router makes a decision, according to all the things that it knows already. It sends the request to a vLLM, to a model server pod, which basically delegates the prefill phase to a prefill dedicated pod, because it knows about prefill-decode disaggregation. When the prefill pod has done its thing, it sends back the result to the decode pod, which does decode. How is this done? The decode pod pulls the KV cache using Nixel. Nixel, I mean, it's not so interesting, but basically it's just a high performance KV transfer library. It's direct RDMA, so it's GPU to GPU copy. There's no overhead or anything. It's quick. As I was saying, PD improves latency. So the blue spots are the aggregated setup. The red spots are the disaggregated. You can see that the inter-token latency doesn't grow as much as the aggregated setup. So, this is quite useful. Like in streaming, application like chatbots, for example. Okay, now I have a live demo. I hope this works, because this is, I'm using a cluster in the US, so hoping there's no AWS outage right now or anything like that. Just to give you like an overview, I'm reading because I don't remember all this stuff. We're going to deploy the intelligent inference scheduling well path. We're going to have 4 pods, each with 1 GPU, so tensor parallelism 1. And we're going to use guide llm, which is a tool for benchmarking inference, which is going to simulate a chatbot workload with a shared system prompt. So I think it's pretty similar to what you would do like when you're coding. Usually you're open code or whatever, they have a system prompt and you have conversations, right? What guide llm does is you have a fixed 500 token system prompt shared among all conversations. Each conversation has 5 turns with 50 unique tokens per user and 256 output token for the response. We're going to have 64 concurrent conversations at any time. And first, we're going to see how does it go with like a normal Kubernetes service, so load balancing, normal scenario. And then we're going to use llm-d to do the same thing. Now I have to move this over. No. Okay. So I built a TUI that basically displays, well, Cloud Code built a TUI that basically displays metrics. It's just going to just cover a little bit of things. Basically, this is just a fancy interface. Okay. I'm not sure how visible it is, like the numbers. I'm going to talk through them anyway. So you see the 4 pods, right? The left part is the Kubernetes service. I'm going to we're going to run it. We're going to write llm for 3 minutes, pretty much. And we're going to see live like how we do in terms of like TTFT, time to first token, inter-token latency, cache hits, token throughput, and all of that. I think it's starting now. Okay, so you can see popping up that we have, I think the most interesting thing for this demo is TTFT P99, so percentile 99, because like that's the tail latency, right? So like that's the worst case that you can have. Like maybe you have a lot of concurrent users. There's 1 user out of 100 that sees this much latency for doing a request, 5.5 seconds, which is not very great, right? Just staring at the screen for that much. We can see KV cache utilization is pretty low. I mean, this is like a micro benchmark, so you know, take as what it is. I mean, I couldn't do anything better. But the cache hits that we're getting is among like 30% on average. Of course, we're building up the cache, but it's going to stay pretty much like this. The load is pretty even. This is not improving so much. P90 is 166 seconds. P50 is 150 milliseconds. We're getting around like 8.5 requests per second and 200 tokens per second in terms of throughput. We're gonna run it for a bit, and then we'll do the same thing for llm-d. Since this takes a while, I can start answering questions because after this we're done. So if that's okay, we can see if there's a question while this runs. Thank you.
Thanks. Super interesting talk. I would be curious, you mentioned that PD distribution, that you switch that to different nodes. Did I understand it correctly that it might be feasible to have then completely different GPUs for the both tasks?
Yeah.
And are you aware that already manufacturers have built dedicated hardware specialized for that, or is that at the moment more something? Yeah, I'm using like the older cards for this and newer cards for this, or?
I mean, manufacturers, not sure. I don't think you need it anyway. Like, you just use the same GPUs, right? I mean, you can use different GPUs for prefill and decode. That's the whole point about it. But you still need GPUs, so then they don't have to be different. But the point is, like you said, for prefill, for example, you might use newer GPUs because they're better at flops. They have more flops. For decode, you don't need that. You just need to have a lot of memory bandwidth. So even older GPUs, and then you multiply the memory bandwidth pretty much by having a higher tensor parallelism, you can achieve great results in terms of latency. So yes, it does allow for different GPUs.
Okay, super cool. Thanks.
Yeah, thank you. Just a second. I'm going to switch over to llm-d now. And we can see that TTFT P99 is around 5 seconds, cache hits around 30%, and we can do almost 10 requests per second. So now we're going to see live how llm-d does. The seeds for the benchmarks are different, so it's totally different conversations that are happening. So we're not leveraging the cache produced in the first phase that I'm not cheating. Also, I'm going to give you links at the end of it, but this llm-d demo, I published it on GitHub, so it's open. You can reproduce it on your laptop or wherever you, I mean, laptop if you have a big, beefy MacBook or whatever, but you can do it somewhere where you have the capabilities. So, sorry, next question.
I have like 2 questions.
Yeah.
So this demo, is this using like OpenShift AI basically on top?
Yes, I mean, I work around. I mean, I'm not advertising OpenShift AI or anything, but yeah, it's part of our offering, yes.
Because it packages it in. So is it possible where you're able to also like share this across namespaces?
You mean what shareable?
Like you have now a common model, let's say, because I have like two questions. One is like, so you have this like quite resource intensive task and you want others like.
Sorry, there's no audio.
Hello. Okay.
Okay.
It's back again. So you might have other like services running, but they want to utilize the same kind of deployment because, you know, if you look at this like RDMA and all this, where you can share across physical nodes over the network, it means that you don't have these siloed implementations of AI agents.
That's an interesting question. Like the llm-d deployment is namespaced. So of course, like the inference pools and everything is namespaced, so you live in one tenant. But the thing is, it's not like a standard, you know, L7 proxy. It integrates well with the gateway API and all of that. So since you need like an HTTP route to expose the endpoint, I'm pretty sure you could have like a HTTP endpoint that's reachable from any of the internal tenants, and maybe you can trick it that way to use the same inference pools. I mean, it could be interesting to take a look at it, but probably you could do it, yes.
Okay. And second last one, similar to his one regarding other hardware, what about like CPU-based models?
Yeah, you can run them. I mean, anything that vLLM supports, yes, you can run it.
So it's not limited. Thanks.
All right. Thank you for the presentation and the depth of it. I have a business-related question. So imagine if I would like to run this setup and offer it to my users to a certain user size, let's see, not too small and not too big. So this makes the setup that I don't like economic-wise, it would make more sense to run with multiple GPUs than with one. So basically with one GPU, I would lose money or I would pay more for the token than if I would have like, let's say 5, 6 GPUs. Suppose they're 100% load and everything, right?
So the question is like whether it makes sense to have multiple GPUs or a single one?
Okay, so the output per GPU,
yeah.
If I have one GPU or if I have 10 GPUs, is of the 10 GPUs, not 10 times more, but more than 10 times, right? Than one GPU.
Yeah, well, of course, it depends on a lot of things, right? So the models of the GPUs, the variant of the GPUs, the models you're running on them, and all those other things. So it really depends. But of course, what I can tell you with llm-d, even if you have with a single GPU, it doesn't make a lot of sense. You could just use like a single vLLM deployment and that's it, because this is about distributed, right? Yeah. So where you have this, when you have distributed vLLM deployments, how to you fully utilize the GPUs. But if you're going like 2 and higher, what I can tell you is that llm-d employs all this optimization and all this, valley path that I've talked to you about to make sure that basically your cost per token is getting lower because you're utilizing the GPUs to their full extent.
Exactly, that's what I wanted to know. Thank you.
Yeah. Okay, llm-d is done. We cannot see the numbers. I'm gonna have to make this very small, sorry. Okay, P99 TTFT is 320 milliseconds. TTFT for the service was 5 seconds, so that's a speed up of 16 times. That's pretty good, I'd say, even for like as a micro benchmark. In reality, these numbers, possibly they might get even better, because like the more concurrent requests that you have, the better use of the KB cache and the GPUs that you do. Inter-token latency P99, it's 25 milliseconds, but like in this valley path, we're not actually optimizing for ITL, but we're more optimizing for TTFT because like we're saving on the prefill cache hit or cache miss. But anyway, we're getting a better number because for llm-d it's 25 milliseconds. For the Kubernetes round robin approach, normal 100 milliseconds, so that's 4 times better. Cache hits, you can see 85% versus 32%, so it's intelligently routing between the available model servers. And we're getting, even in this small micro benchmark, a 15% more requests per second and 15% more in terms of throughput, like token per seconds that are generated. Again, this is a micro benchmark, so take it as this, but it shows that llm-d is better at making use of those metrics that are produced by vLLM and routing intelligently. And also, if one interesting thing, I think, you might get tricked into thinking like, okay, because llm-d is just redirecting all requests to the pods that already have the cache. Yes and no. We've seen that the intelligent inference scheduling welded path is composed of the load-aware part and the KV cache-aware part. So actually, we see that the load is evenly spread, even when using llm-d, because it's 25%, 24%. This is the number of the requests that we're processing. And it's about the same as the other one, as using like the standard Kubernetes service. Why? Because we're still optimizing in terms of load and KV cache utilization and all of that. So I think that's pretty good as well. Okay, this is the end of the demo. So thank you. Thanks. Do we have time for other questions?
I have one.
Yes.
I've seen on the intro picture you were mentioning LM cache. So
Yes.
wouldn't it be simpler to just say, hey, we're just going to use LM cache and attach LM cache to all the nodes instead of adding specific routing functionality as with that demo?
LM cache takes care of offloading. It doesn't take care of like routing the requests. So it's a little bit of different scope. That said, vLLM supports LM cache, so you can use LM cache with vLLM and hence with llm-d. vLLM is building, maybe they have done it already, I don't know, their own offload connectors, so their own like internal implementation of LM cache. So you can just use it right out of the box without relying on LM cache.
Okay. Cool. So we have to give that a try. Another question there.
Yeah, I would have questions all afternoon, but maybe I can squeeze in two. Similar with the LM cache question. So I think a lot of this, what we've seen, like the different kinds of routing, is done by vLLM production stack. So if I use this today, can you convince me to switch to llm-d?
We're gonna have a long conversation, I think, but no. But the point is very shortly that I think that is meant to be like a sample of how you should do things, like a blueprint, right? I don't think it's geared towards serving enterprises deployments. With llm-d, that's what we're doing. I mean, and I think like that predates llm-d as well. So it is kind of like a conversation that's continuing in a way.
Okay. Nice. And if I can squeeze one in, but for all the bigger models, like the frontier open ones, like GLM 5.1, that's so big, I think probably prefill this decode disaggregation is the only way to actually run them at any kind of speed. But people don't necessarily know how do we split this. So how would you tell people to, like, how would you, without spending too much effort on it, how to do the PD disaggregation without,
I mean, it's two questions in one, I think. To run those big models, like for example, DeepSeek, it's a mixture of experts model, which are huge. llm-d, we have a specific well-lit path for it, which is called the YDP, if I recall correctly. I didn't include it in this talk, otherwise it would take too long. But you can look it up on the llm-d website, and basically what it does, it simplifies the deployment of those models, because how it does it uses the leader worker set capabilities in Kubernetes. I think it's like a separate controller or something like that. But it shards the model between different nodes. So because like the amount of GPUs that you have in one node, that they're not enough, right? So it shards divides the model pretty much like in different nodes, and then architects all the KV cache pooling and prefill-decode orchestration together with vLLM. So that's way of doing it. So we have a welded path for it, basically.
Nice, thanks. I'll let others ask if they had any more questions. I'll reach out to you later then.
Well, I'm here for today and tomorrow. So, any questions, any conversation, I'm really happy to talk about it.
Then thank you very, very much, Antonio.
Thank you.